Okay, so we're going to start off with some sample diploma problems from last lesson. So, let's just get my pen working. A path of charged particles traveling perpendicularly through a uniform magnetic field is deflected due to blank, and the speed of the particle will be blank. So, if particles enter a magnetic field, this is our magnetic field, what's going to happen is they're going to get deflected, and then they're going to move in a circle like that. So the reason they move in a circle is because there's a magnetic force, and that's it, right? Fc is equal to Fm is all we are. So it's an unbalanced force, right? So it's an unbalanced force, and it stays at the same speed, right? The speed stays the same. The velocity changes in terms of direction. It's accelerating, but A is going to be our correct answer. Okay, in 23, which the following diagram shows the orientation of the magnetic field must have in order to deflect the particles. Okay, so we need to know what type of particle it is, and it's saying that it's protons. So you have to be really careful with this one, and you have to use your right hand. That's the biggest mistake that people are going to make. Okay, so I'm going to switch over to this. So we want our protons to be traveling in this path, right? So we want our magnetic force to go towards the center of the circle. So if I put my thumb of my right hand this way and I put my palm going this way, you can see that my fingers are going into the page. So we're looking for a magnetic field that is into the page. So into the page are X's like this, so that makes C the correct answer. Electrons are accelerated from rest by an electric potential difference. Oh, this is a big one. These electrons enter a region that contains mutually perpendicular electric and magnetic fields. Okay, so it's got two types of fields. So we want to find the acceleration. Okay, so I'm going to switch to my other screen. Okay, so there's two parts to this question. So the first part of the question is we have plates. Actually, let's start up top so I have a little bit more room. So we have plates, and they are electrons. So this plate is negative. This plate is positive. And then we put a little hole in the plate so my electron travel through there. So we've done questions like this before. This is a law of conservation of energy question. This is physics principle number 5. Yeah, energy. Where here we have EPE, and this is turning into EK. That's the first part of this question. Right? The second part of this question is we go between two different plates. So in the second part of this question, I have a positive plate up here, and I have a negative plate down here. So when my electron is in between here, it's going to experience a force upwards because it's going to be attracted to the positive plate. So that's my electric force, but we know from the diagram in the question that it deflects downwards. So there must be a bigger magnetic force downwards, and that magnetic force is going into the page, right? And if I use my left hand, I put my thumb this way, my fingers going that way, you can see that it deflects it down. So my force magnetic is bigger than my force electric. And because it's accelerating down here, we can use physics principle number 1. And that's the answer to the next question. We got to use 5 and 1 or 1 and 5. Okay, so let's start with the second part because we want to find the acceleration. That's what we're looking for. So we can write an F net equation for this. I'm going to make down positive and up negative because the net force is down. So it's going to be force magnetic minus force electric. Okay, we can break those down into MA. My force magnetic, because it's a charged particle, will be QVB, and my force electric will be EQ. And they give us an electric field, so we don't need to break that down. So we just need to move our mass down there, and we are good to go. So we know the charge of the electron. We don't know the speed. It's not given in the question. We know the magnetic field, we know the electric field, we know the charge, and we know the mass of the electron. So we still need our speed, and that's where we get it from physics principle 5, where we can say that our energy before equals our energy after. So we have EPE is equal to EK. EPE is equal to VQ. EK is 1/2 mv squared. So I'm going to move the 2 up top, the mass down below, and square root it, and I can find my speed. Okay, so 2 times my voltage, which is 3 times 10 to the 2 volts. 1.6 times 10 to the negative 19 coulombs is my charge of my electron, and 9.11 times 10 to the negative 31 kilograms is the mass of my electron. So I square root that, and I have a fancy dancy on-screen calculator because I'm back at school. So I'll plug all that stuff in here. So 2 times 3 times 10 to the 2 times 1.6 times 10 to the negative 19 divided by 9.11 times 10 to the negative 31. I square root my answer, and I get my speed to be that. Okay, so now what I'm going to do is I'm going to finish off the question by plugging in. Now that I have the speed, I can plug in all the rest of this stuff. So my charge, 1.6 times 10 to the negative 19 coulombs. My speed is at 102.65413. I'm going to use my last answer, so that's fine. And then my magnetic field is 2 times 10 to the negative 1 Tesla. And I'm going to subtract my electric field, which is 8.5 times 10 to the 5 Newton per Coulomb. And then my charge is 1.6 times 10 to the negative 19 coulombs. And I just made it on the screen. And the mass of my electron is 9.11 times 10 to the negative 31 kilograms. And I think that is all. And we should get a nice positive acceleration when we plug that all in. So we got to use our brackets. 1.6 times 10 to the negative 19 times my answer from before times 2 times 10 to the negative 1. Yeah, and then we're going to subtract 8.5 times 10 to the 5 times 1.6 times 10 to the negative 19, and then divide that all by the mass of the electron. And it should be a big acceleration because it's an electron, so having a big one is not strange. And we get 2.11 times 10 to the 17. So 2117 is the answer that they're looking for. Okay. And then for the next question, so we used 1 and 5 to answer this, or 5 and 1. The order doesn't matter. Okay, so those are the sample diploma questions. So now we're in our last lesson, which is a weird lesson, and I wish I didn't have to teach this virtually, but what can you do? So we're going to describe how the discoveries of Oersted and Faraday form the foundation of the theory relating to electricity and magnetism. We're going to describe qualitatively, so without numbers. There's no numbers in this one. The effects of a moving conductor in an external magnetic field, and predict using appropriate hand rules the relative directions of motion, force, and field. So we're going to learn a new kind of new hand rule. Yeah. So motors. So DC means direct current. So direct current motors take advantage of the fact that two current carrying conductors attached to the same direct current can be made to generate B fields in opposing directions. So what that means is that if I have current, so this is negative, this is positive, so if my current is going here and then it goes into the page here, if we use our third left-hand rule, and our magnetic field goes from north to south. So if you hold up your hand and you put your thumb into the page and then you put your fingers of your left hand to the left of the screen, you'll see that your palm is downwards. So we end up getting a magnetic force downwards. So as the current goes into the page, it goes through here and then it comes back this way. So now if you put your fingers to the left of the screen, but you have your thumb coming out of the screen, then you end up getting a magnetic force upwards, right? So what that means is if this one is pushing downwards and this one is pushing upwards, what you can do is you can get this to rotate in a circle. And that's basically how a motor works. A motor uses magnets and current, and it makes it move in a circle, and that's pretty much it. But motors aren't really the focus of Physics 30. What we're more focused on is generators. So the difference between a motor and a generator is a DC motor, direct current, allows electricity to produce motion. Okay, so what we're more concerned about is a generator, and that uses motion to produce electricity. So the process of using motion to produce electricity is called electromagnetic induction. So I have a video here that I'm going to show you, and you can see this idea. I wish I could show you in real life, but this is the best I can do with this video. So here is the video. So what's happening in that video is you have your copper tube. So let me just draw what's happening in there so we can explain what's going on. So you have your magnet. So that was a silver thing. You have north and south. So our magnetic field goes from north to south like that. But if we want to focus on this side over here, it's going to go away from the north. And then we have our copper tube. So the reason that the copper tube is moving is because copper is not magnetic. It has nothing to do with the fact that magnets are attracted to metals. It's not magnetic. It wouldn't work if it was magnetic. The magnet would just stick to it. But what happens is we end up getting electrons moving through this copper pipe, and that current is induced by the magnetic field from the magnet. And depending if he moves it towards or away, what would happen is that the electrons would move in the opposite direction if he was moving it away. And when those electrons move in there, they create their own magnetic field that sort of wraps around and opposes the motion of that magnet. So I'm going to explain a little bit more of how that works, but that's what's happening. So the magnet induces a current, the current creates a magnetic field, the magnetic field opposes the motion of that, and that's why you can get it to move. Okay, so let's go back to the PowerPoint. Let's talk a little bit about electromagnetic induction. So this occurs when an electric conductor moves through a perpendicular magnetic field. Okay. So the motion is due to the force applied. So what we have here is we have a wire. And what I'm doing is I'm taking this wire and I'm moving it down through this magnetic field that's coming out of the page. So I'm applying a force downwards and I'm moving this wire downwards. So we're going to start with the straight wire because it's just a little bit easier. So when I move a wire not connected to anything through this magnetic field, what we'll get is we'll get current flowing through the wire. But what we don't know is we don't know whether that current will flow clockwise or counterclockwise. So that's what we're gonna figure out. So to figure that out, we need to use Lenz's law. And Lenz's law says that the direction of the induced current will produce a magnetic force as to oppose the applied force producing the original motion. So I'll explain what that means. So what I'm doing is I'm taking this wire here and I'm moving it downwards. I'm just taking a straight wire and I'm moving it downwards. Okay. So this is my force applied. My magnetic field is coming out of the page. So I'm just going to draw that on here. So this is my B field that's coming out of the page. So what Lenz's law says is that if my force applied is down, well, my magnetic force is going to oppose that, and my magnetic force is going to be upwards. Okay. So what we want to do is we want to take our hand and we want to stick our fingers out of the screen. So stick your fingers away from the screen that you're looking at, and then make sure that your palm is facing up. And when you do that, we want to take a look at the direction of our thumb. So if you're doing this correctly with your left hand, fingers coming out of the screen, palm facing upwards, you'll see that our thumb is going to the right of the screen. So this is the direction of our current. So our current is going to move to the right, which means that our current is going to move in a clockwise manner around this wire. Okay. So that's one way of doing it, and that way it would work. But what we'll also learn is we'll learn a third left-hand rule prime, which is just a little bit different. Okay, so to find the direction of an induced current, fingers point in the direction of the magnetic field, so that's no different than our regular third left-hand rule. This is the different step. So our palm is trying to stop the conductor. Right? So the conductor is moving this way, and then my palm is saying stop. And then the thumb points in the direction of that induced current. Okay. So I have another video here, and this video reminds me of what this is like. It's kind of like using the force with the third left-hand rule. So here's a little clip of Star Wars. Yeah.
Master Yoda.
Count Dooku.
You have interfered with our affairs for the last time.
Powerful you have become, Dooku.
So in that video, Yoda was kind of using the third left-hand rule prime. So think of the objects that were being thrown at him. He was using his hand to try to stop that, and that's exactly what the third left-hand rule prime is doing. So let's do an example here. So you can see that our magnetic field is coming out of the page. Our wire is going to the left, and we want to indicate the direction of the current through the resistor. Okay, and this is a resistor right here. So I'm going to switch screens. I'm going to draw out what's going on. So we have our magnetic field that's coming out of the page. And what we're doing is we're taking a wire and we're moving it this way. Okay. So first thing I'm going to do is I'm going to use my left hand, and my fingers are going to point out of the page, right? And this is my, I'm going to dot this line because this is my actual wire here that's moving. So first thing you're going to do is you're going to point your fingers out of the page like that, right? And we can rotate, oops, I'm off screen. And we can rotate like that, so our fingers are coming out of the page. Okay. So if this wire is coming towards me and I want to use the force to try to stop it like that before throwing it back out there, the only way I can do that is have my thumb pointed downwards, right? So that's the direction of my current, is my thumb is pointed downwards like that. So that means that my current, my electrons are going to flow that way, downwards, like that. And this wire is a loop in the picture. So here's the resistor over here. So it's going to travel that way, and it's going to go in a circle like that. So my electrons are going to go down. So it's actually going to go up through the resistor, but it's going to go down closest. And that's what we want to look at. What's happening closest, and closest it's going to be going downwards. Right? So hands up. You could be pointed away, but then you're not going to use the force to stop it. You need to go like this, stop it, and your thumb is pointed this way, which means that it's going to be downwards. Right, so the current would move downwards across the resistor and then upwards through the resistor. Okay, so hope that helps. It's kind of a tricky idea. Students have trouble with that one. So Ørsted was a scientist. He found that moving currents produce magnetic fields. That was the very first thing that we did, the very first hand rule. So if you send a current through a wire, that magnetic field circles around it. Faraday, who was another scientist, examined the opposite, and found that B fields, magnetic fields by themselves, did not induce currents. So if you just have a magnet by a wire, that magnet will have a magnetic field. You wouldn't get a current moving through there. What you need to do is you need a changing magnetic field. This is the important thing. If you have a changing magnetic field, that causes a current. So that's why things are always moving in this. So only when a conductor cuts through a magnetic field or a magnet moves near a conductor will we get electromagnetic induction. So I'm going to show you using the simulation here. So, yeah, this is the one that I want. So here we have a magnet, and here we have some wire, and I'm going to show a field meter. This doesn't really matter what these symbols are, but you can see this shows our magnetic field, and my magnetic field is not changing. So if I put a magnet by a wire, I don't get any current moving through there. But if I take this and I move it near this, right, you can see that now that I'm moving it, my magnetic field is changing. And when my magnetic field is changing, that's when I get current moving through the wire. So as soon as I stop it, it does nothing, but I move it, whether it's forwards or backwards, and I get current moving through that wire because my light bulb lights up. Okay, so this is the idea of how a generator works. So what we need for a generator is we need a changing magnetic field, so a moving magnet, or I can move these guys as well. So if I move this near my magnetic field, because I'm changing that magnetic field, that works as well. So that's how a generator works. So this is just a very simple generator. So here I have a magnet, and I can use something like water to move my magnet. And if I move my magnet near my wire, I produce electricity, and that's how hydroelectric power is created. Okay, so let's do a different type of example. So Lenz's law also applies to coiled conductors and the resulting magnetic fields from any induced current inside of them. So any magnetic field produced will oppose the motion of the applied force. Okay, so a couple different things that I can ask in this question. So remember that if we have a coiled magnet or a solenoid, it works just like a bar magnet. So I drew this bar magnet inside. So what we can figure out is we can figure out the direction of this bar magnet, and we can use our second left-hand rule to figure out the direction of the current in here. So if I take a magnet and I move it towards here, what's going to be set up inside of here is it's going to be set up, it's going to set up a magnet in order to oppose the motion. So it wants to repel it. So if I set up a south here and a north here, well, that wouldn't oppose the motion, right? Because if I'm moving this magnet this way, well, if the south is set up here, it's going to get easier as I do this, and it's going to attract it. So that's not correct. That's not what we want. So what we want to set up is we want to set up the opposite. So we want to repel it always. That's what Lenz's law says. So if we set up a north here and a south here, that's going to repel it, and that's going to make it difficult to bring it towards here. And now, if we use our second left-hand rule, so I'm going to switch screens so we can see my hand. With the second left-hand rule, you want to focus on the wire at the very end or the very beginning. And you can see at the very end of it here, so we said that this is north and this is south, this wire goes behind. Right? Or I could focus at the very beginning where the wire goes on top before bending down there. And then we have an ammeter down here. So I'm going to take this. This is my electromagnet. This is what I'm doing. And I want to make sure that my thumb points this way. So if my wire's behind, you can see that my fingers are pointed downwards. And if my thumb is pointed this way, and if my wire's on top, so I put my fingers on top, you can see that they're moving up. So on top, they're moving up, and then down below, they're moving downwards like that. So you can see that's the direction of the electricity across the ammeter. So it's moving to the left. Okay, so let's try another example. So to determine the direction the current would flow across the galvanometer. And a I always want to call it a galvanometer, but I think it's a galvanometer. So inside of here is a bar magnet. So if we're moving south towards, then that means it wants to oppose. So south would be set up here, and a north would be set up here, right? This drawing isn't very good. I need to replace this drawing, but this one moves behind and this one moves in front like that. That's why it's better to sort of draw a course so you can see that better. So I'm going to focus on right here. Okay, so I'm going to grab my pen and I'm going to hold it up. I want you to do the same thing. So grab a pen, hold it up to the screen. I want you to point the thumb of your left hand towards the left of the screen, because that's where I drew an arrow on here. Sorry, get rid of this arrow. So put your thumb to the left of the screen, and I want you to put your hand so that it's on top, so that it's further from, so that it's like your screen, your pen, and then your hand like that. And you can see when you do that, your fingers point downwards, which means that the current must be going downwards. You can test it out on this side. So keep your thumb pointed this way, and then put your fingers in between your screen and the pen, right? So put it behind your pen, and you can see that the current is moving up. So it would move across the galvanometer like that. It would move to the right. That'd be the answer. Okay, there's more homework questions like that. Give it a go. Try your best. Let's just bring up this simulation one more time, and we'll take a look using that. Just going to get rid of this. So this is the same idea. So what I'm looking to do is, I don't know how I can draw on this. I don't think I can draw on this. Anyway, so you just have to listen to my voice. So we will, I can't draw on it. So if we bring the north end towards my coils, right, that means that inside of this electromagnet, a north will be set up on the left side and a south will be set up on the opposite side, but we want to focus on the north. So the north is going to be over here. So take your thumb of your left hand, point it towards the left of the screen, right? And then if you grab onto a pen or something like that, you can see that when you're in front of the pen, your fingers are moving down, and when you're behind the pen, it's moving up. So according to this prediction, if we move the north towards it, on this side here, our electrons should move down. And they do. Right? If I move it away, it's going to try to oppose that motion. So over on this side, a south is going to be set up because the south is going to oppose the motion. As I'm moving away, you want it to attract. So the south is set up over here. The north is set up over here. So put your thumb to the right side of the screen. And as you move away, if you are in front, your fingers should be moving up. So as I move away, my electrons should be moving up, which they are. Let me just try that again. Yeah. So towards they move down, and away they move up. Yeah, better in person, but that's the best I can do. Okay, so I'm going to do this sample diploma question right now, and students struggle with this one. So you pause the video, give it a go on your own, and we can go through it together. So it says that you have a copper ring is suspended by an insulating string, and a north pole is coming towards it. It's going through it. So the first thing I'm going to do with this is I'm going to draw a different view. I don't know why my pen does that. It always skips up like that. So like that. So that's kind of a 3D picture. So I find the side view is helpful. So we have north and we have south, and we're going to be going that way. So I took this picture and I sort of rotated it towards here. I don't know. I hope that helps. Anyways, so we're bringing the north towards. So that means that a north is going to be set up over here, and this is a south set up over here. This is the ring is just like a coiled conductor, so it's going to be set up like that. So no matter what, the north end of this permanent magnet, this magnet, is going to be going towards this. So if we have a north here and a north here, that's what Lenz's law says. It's going to be the opposite. If this is what we set up, then these two are going to repel. So what's going to happen is this string is going to swing away, and that's kind of what we saw in that video that I showed you with the copper wire and the magnet. So this string is gonna swing away because they're gonna repel. So the ring swings away from the magnet, and it'll always oppose it. It'll always go the opposite. Okay. So the magnet and the electron flow at point P. So this is where we want to use our second left-hand rule. So point your thumb to the left of the screen because that's where our north is, and then maybe I'll switch screens for this one. Oops. So we kind of have it like this, and then we have north and south. So a north is set up here and a south is set up over here. So what that means is I hold my pen up, I point my thumb this way, so my fingers can either go underneath or they can go on top, like this. Just gotta switch angles. There we go. So here's my pen, so they can go on top, or they can go underneath like that, right? So I always want to make my thumb point this way, right? Because that's the north end. So if I'm on top, it's moving downwards, like that. And if I'm underneath, it's moving upwards. So that's sort of the direction of my circle. Okay, and point P is right here. So at point P, it's going to be moving downwards. Right, so it's going to move downwards towards the bottom. Okay, move upwards here, and it moves in a circle. So B is the correct answer. Okay, so here's your homework. Here's some review. We're just going to do a quiz on magnetism and not electricity. I don't know how this whole grading thing is going to work, but yeah, we're just going to do a quiz on magnetism on Thursday. So we'll see how that goes. I don't know. Okay, if you have any questions, feel free to message me. That is all.